Hi there, welcome back. So, what we will do in this lesson is to continue dealing with the analysis of tails in empirical data, and we will also consider the problem of the estimation of the parameters we might be interested in, like for example the t parameter xi. Now, in the previous lesson, we introduced some interesting tools like the ZIF plot, so the log-log plot of the empirical survival function, and the mean excess function plot, or ME plot. And we saw that using those plots, we can try to understand a little bit more the behavior of the tail of our random variable. Remember that we are considering a random variable that, to simplify the treatment, is a non-negative random variable. Again, by using the change of sign and all the rest, we can focus on the left tail as we do for the right tail. Okay, so we are considering these graphical tools, and we saw that both the ZIF and the ME plot can be used, for example, to try to have an educated guess about the threshold above which we can suspect to have fat tails. That is to say, to have this Paretian behavior, that is to say, where we have this power law decay. In a sense, we are looking for all those distributions for which the survival function is regularly varying, as we have said when we gave a definition of fat tails. We saw that there are distributions that have a clear behavior in both the ZIF and the mean excess function plot, and that in both plots the tricky objects are always the power law, or the Pareto, and the log normal. In principle, it is difficult using just a few data points to observe a clear difference between the Pareto and the log normal. In any case, what we are looking for is some sort of linearity. In the ZIF plot, we look for a negative linear behavior. In the mean excess function plot, because of the van der Waals law, we look for an increasing linear behavior. And we have said that a way of finding the threshold for the fat tails is to look at the point at the level of the variable for which at a certain point we observe the linear behavior, be it the negative linear behavior in the ZIF or the upward linear behavior in the ME plot. In reality, we have many more tools that we can actually use to go deeper into the understanding of the tail. Now, one plot that I want to discuss with you for sure, because it is extremely useful, is the so-called maximum to sum plot. This is a plot that relies on two important things that you know. One is the law of large numbers that you remember from your basic courses in statistics, and the other one is the catastrophe principle that we essentially entered in the discussion when we were dealing with the sub-exponential class of distributions. Using the law of large numbers and the catastrophe principle, we can say something about the theoretical moments of the random variable that we are considering. And knowing the behavior of the theoretical moments of the random variable we are considering is essential to have a correct modeling of our phenomenon. Even if it can be tricky from a practical point of view to distinguish between a Pareto distribution and a log normal distribution with a sigma parameter that is large enough, because the mean excess function plot and the ZIF plot can be misleading in the sense that both they show some sort of linear behavior, and only a lot of observations can help us in discovering the closing concave behavior that log normal has in both plots. Okay, even if in practice it can be difficult to distinguish between the two distributions, there is a fundamental difference that we never must forget between the Pareto and the log normal. The fact is strictly connected to the characteristics of the distributions we are considering. What we know is that the Pareto is in the maximum domain of attraction of a free shape, while the log normal, despite being such a tricky and wild animal, is in the gamble class. So it's in the maximum domain of attraction of a gamble distribution, together with other distributions like the exponential and the normal. So a fundamental difference between a Pareto and a log normal is the existence of moments. Depending on the value of the parameter alpha or psi, depending on the parameterization you use, the Pareto distribution can have infinite moments. So, for example, if we use the alpha representation in which we have that the tail is x to the power minus alpha, then in the Pareto case, if alpha is larger than 2, the second moment is finite. So the variance is finite. But if alpha is smaller than 2, the second moment is not finite. It means that it does not exist. So we have that the theoretical moment of the distribution is not properly defined. We are considering a phenomenon that is extremely erratic, that can generate very large variations, and the variance, the theoretical variance, is infinite. The same if the parameter alpha is smaller than 1, even the first moment, so the mean is not finite. And we are considering a so-called infinite mean phenomenon, which is the most dangerous type of phenomenon you might encounter in the analysis of data. If the parameter alpha is larger than 3 but smaller than 4, we have that, for example, the third moment exists, is finite, so we can compute the skewness, but the fourth moment, something like the kurtosis, is not finite, is not defined. So in principle, you have that the moment of order p exists, is finite, only if alpha is larger than p. So if the moment of order 2 is finite, it means that alpha is larger than 2. If the moment of order 3 is finite, it means that alpha is larger than 3, and so on. Now, what does it mean then the theoretical moments are not finite? If you look at data, and this is a very important misunderstanding, if you look at data, you will be always able to compute the moments of your data set, of your sample. In-sample moments are always finite quantities because it's just a matter of computing the mean, the variance, the skewness, the kurtosis using simple formulas. So you will get a number. The point is that the theoretical moment might not be finite. And if the theoretical variance is not finite, the sample variance you are computing is essentially useless because you cannot make inference using it. So if you compute the sample variance tells you nothing about the variance of the theoretical phenomenon because that variance is not finite. So focusing your attention on the sample variance is useless. And notice that even if the second moment is finite, if the fourth moment is not finite, what happens? It happens that it is difficult to build confidence intervals for the variance. So it is not just a matter of the existence of the specific moment you are considering, but also higher moments can be important. If the first moment is finite, so the mean exists, and you can compute somehow safely the sample mean, but the second moment is not finite, so the variance is not finite, it means that also the standard deviation is not finite. And then you immediately understand that it's not so easy to build the usual confidence intervals around the mean. So it's always very important to deal with moments. Okay, if you consider a Pareto distribution, some of its moments can be infinite, cannot exist, depending on the value of the parameter of the tail. Conversely, a log normal can be extremely wild, can be extremely erratic because you have a sigma that is very large, yet all the moments of a log normal random variable are finite and exist. So you may be interested in the moment of order 20, it exists and it is finite. It is not important the value of sigma. A fundamental difference between the Pareto and the log normal is the existence of moment. For a Pareto, some moments might be not defined, so they could be infinite. For a log normal, they are always finite and there. So this is an interesting difference that actually we can exploit. And one of the plots we can use to exploit this difference is the maximum to sum plot. So given a sequence of IID random variables x1, x2, x3, and so on, what we can do is to define two quantities. One is the quantity S and P, and the other one is the quantity M and P. Now, if you set P equal to 1, these quantities are S and 1, which is nothing more than the partial sum, and M and 1, which is nothing more than the partial maximum, as we have defined them before in our course. If p is larger than 1, and p can be obviously 2, 3, 4, 5, we are considering integers. Okay, for higher p's, what we have is a sort of generalization of the concept of partial sum and partial maximum on transformations of our variables. For p equal to 2, what do? We take all our observations, we square them, and then we take the partial sum. If we do for the partial maximum, we square them and we take the partial maximum, and so on. So this is what we do. After computing for different quantities p, so for different values of p, after computing the quantities S and P and M and P, we define the ratio M and P over S and P. This is what we call the maximum to sum ratio of order P. Now, the law of large numbers tells us that the ratio R and P, that is to say the ratio of the partial maximum of order P and the partial sum of order P, will converge almost surely to 0 if and only if the pth moment is finite. So if, for example, the second moment, the variance of our random variable is finite, then we will see that the ratio R and 2 will converge towards 0 with n growing. So the more observations we consider. So what we can do is the following. Now assume that we have n observations in our sample. Now let's start from the first one. Please notice that I'm not telling that we have to order the observations. These are the observations as we have collected them, okay? Now, just focus on the first observation. Necessarily, the first observation is both the partial maximum and the partial sum when I only consider one observation, trivially. Then I consider the first two observations and I compute the partial sum and the partial maximum. And then I consider the first three observations, and again I will have the partial sum and the partial maximum, and this for all the observations. And I will do that for the different p's. So for p equal to 1, I just consider the observations as they are. For p equal to 2, I will square the observations. If p is equal to 3, I will take to the power 3, and so on. And what happens? I can build a plot in which on the x-axis I put the number of observations I'm considering. So n, from 1 to the actual number. And on the y-axis, I can put the ratio R and P. Now, if the moment of order P is finite, I will see that for the number of observations growing, the ratio will decrease and will tend towards 0. So initially, I may have some oscillations because obviously I'm just considering a few observations, but the more observations I'm considering, the more the ratio will tend to 0. If conversely, the moment of order P is not finite, what happens? It happens that the ratio for the corresponding P, so the RMP ratio, will be extremely erratic and it will oscillate and will not converge towards zero no matter how many observations I take into consideration. Now, why it can be useful to use the maximum to sum plot to distinguish between the Pareto or any type of fat tail and the log normal? Because of the fact that for the log normal distribution, we will necessarily observe the convergence of moments. We might need some observations, so obviously with 10 points, there is not much that you can do, especially if you are not lucky and you are sampling the points in strange areas of the distribution. But with a decent number of observations, so we are not speaking about thousands and thousands, but let's say with a few tens or even better, a few hundreds of observations, you will see the convergence of moments for what concerns log normal. In case of a Pareto distribution, if you are not considering a Pareto distribution for which even the higher moments are defined, but in that case then it's not really something particularly risky to model. I mean, a Pareto in which alpha is larger than 10 is behaving, I'm not saying like a thin tail distribution, because technically it is not, but in practice it is. So let's say that we are always considering situations in which, and this is what we observe in actual data when we fit fat tails, we are always considering situations in which the alpha parameter is at most 4. In finance, for example, a very common quantity for the alpha parameter is somewhere in between 2 and 3. So you might have the variance finite, but not the skewness. So already the variance is no longer so reliable because of the fact I was telling you before in terms of the confidence interval. If you go in some areas of risk management like credit risk, operational risk, and also some parts of market risk, the alpha parameter is even smaller. So most of the times it's between 1 and 2. So the variance is not finite. And in operational risk, we will see very briefly that there are even situations in which alpha is smaller than 1. So not even the mean is finite. So in all those situations, it is quite simple to distinguish a fat tail with respect to a log normal, because for the log normal, you will always see the convergence in the maximum to sum plot because of the existence of the moment. So we know that log normal has finite moments. In the fat tail situation, conversely, you will see that for certain p's, then the plot will not converge. And remember that if the moment of order p does not exist, all the higher moments do not exist as well. So if you show that the second moment is not finite, there is no need to show that the third, the fourth, the fifth moment are not finite. It is a trivial consequence of the fact that the lower moments are not finite. Okay, let's consider some real data, then later in our R class we will go deeper into the actual modeling, so I want to really show you how to do these things in practice, but for the moment let's consider these plots that you can see here. Now here in the first 4 plots here, I show you some credit risk losses. Okay, so these are losses linked to a portfolio of mortgages in the framework of credit risk. And as you can see here, we have that for sure the fourth moment appears not to be finite, the same for the third. The second one is tricky, as we shall see, and the first one exists because we see a clear convergence towards zero in the maximum to sum plot. I'm telling you that for the second moment it is a little bit tricky because what I want to stress is that even if it is extremely useful, the maximum to sum plot, as all the plots that we will see together, is a first step. Then you have to go deeper into the analysis and, for example, estimate the tail coefficient and discover if alpha is really between 1 and 2, as we could, for example, assume looking at these plots, or if the strange convergence you observe for what concerns p equal to 2 is just due to the fact that you don't have enough observations. And maybe with more observations, it could actually converge. no discussion for p equal to 3 and 4. This is clear that there is no convergence. Here, conversely, you see another example. These are operational risk losses. Operational risk is an extremely tricky risk that we will consider together. It is a type of risk that, together with Nassim Taleb, but also other scholars, we call apparently infinite mean phenomenon, because we will see that in reality, really assuming that you can have an infinite loss in a company makes no sense. If you're a bank, the maximum loss that you can expect, at least from your point of view, is what? Is your value, is your capitalization. So you cannot have an infinite loss. Yet, if you just look at the data, if you let yourself be fooled by data, as I like to say, looking at this plot, you might suspect that even the first moment is not finite, because it is clear that there is no convergence, even for p equal to 1. So even the mean could be not finite. So in this second situation, we are considering an extremely risky phenomenon. Okay, also this one is not at all a safe one, because, I mean, we are saying that variance is not finite. So we are saying that just one observation can totally make your sample variance useless. But here, one observation can make your sample mean useless. Okay, so you are considering the mean of something, and then just one observation makes the mean jump of different orders of magnitude. So this is what we are seeing here. Be very careful with this type of objects. Another graphical tool that I want to discuss with you is a graphical tool that I, together with my co-authors Case Osley and most of all Andrea Fontanari, this is part of his PhD thesis, is a plot that we introduced, that we called the concentration profile. Now, the concentration profile is a diagnostic tool that you can use to study the tail of a distribution, but also to characterize a distribution. So if you do not focus just on the tail, but on a pure distribution, you can use the concentration profile to characterize that distribution. And the tool behind a concentration profile is the Gini index that we have seen very briefly in financial mathematics, that we have also briefly cited in risk management when we deal with the distortion measures, the Lorentz curve, you remember all these kind of things. So let's consider a non-negative random variable. With capital F, we indicate its distribution function, with Q, the quantile function, that is to say the generalized inverse of our random variable with respect to the distribution function F. The only requirement for the concentration profile to be properly defined is that the random variable we consider has a finite mean, which is not at all a very strong requirement. So in most situations in risk management and in finance, the mean of the random variable we are considering, the losses, the profits, whatever you want, is finite. There are only a very limited number of exceptions I can think of, operational losses, and yet I will show you that it is not really possible to have an infinite loss, the number of casualties in wars, the number of fatalities in pandemics, and maybe for sure some other little exceptions, but most of the time it is not a strong assumption to assume that the mean is finite. So the concentration profile actually has a wide range of applications. Given information about the quantile function of a random variable, both the theoretical and the applied, given the quantile function, given the mean, I can compute the so-called Lorentz curve, that we know is this curve that lives in the triangle of vertices 0, 0, 0, 1, 1, 1. So in the lower part of the unitary square. Now, this function is a function that has been introduced in the literature related to inequality studies. It has a lot of nice properties. It is non-decreasing, convex. It lies between two extreme cases that are the perfect equality, the perfect inequality. So we already said all these kind of things. Given the Lorentz function, I can always compute the Gini index. The Gini index is a summary measure of inequality, and it is nothing more than twice the area between the diagonal or the perfect equality line and the Lorentz function I am considering. So twice the area A that you see on your screen, or if you want to express the Gini index in terms of the areas A and B, it's A over A plus B. But remember that A plus B is equal to 0.5, so that's why we can always write two A's. The idea behind the concentration profile is rather simple. We do something similar to what we did for the mean excess function plot. So what we can do is the following. We can order all our observations, okay? And once we have these ordered observations, we can compute the Gini index of all the observations. Then we exclude the first observation and we compute the Gini index of the remaining n-1 observations. Then we exclude the first two observations and we compute the Gini index of the n-2 remaining observations, and so on. So we are computing for different threshold levels the corresponding Gini index. This is what we call the truncated Gini index that can be formalized as you see on your screen in terms of truncation with respect to a given quantile. Okay, so I can always find a quantile corresponds to one of my observations, and for that quantile I just consider the Gini of all the observations above the quantile I'm fixing. This is what we call the truncated Gini. Now, by plotting the truncated Gini against the truncation level, I get the so-called concentration profile. Interestingly, power laws and Pareto distributions are the only distributions for which the concentration profile is constant. So it does not depend on the threshold. Why? Because the Gini of the Pareto is independent from the quantity P. So G of P is always the same. It's just a ratio of the alpha parameter of the Pareto. So it's a constant line. Conversely, other distributions have a different behavior. Another very interesting distribution is the exponential. The exponential, all exponentials, notwithstanding the value of the parameter we use for the exponential, all exponential are exactly behaving as the red line that you see on your screen. Why? Because the concentration profile of an exponential is independent from the parameter of the exponential. It's a function of p, so it has this behavior, but it is independent from the parameter of the exponential. Other distributions, like the variable and log normal, have other interesting behaviors, but you see that it is quite clear the difference between, for example, a log normal and a Pareto. So a Pareto will be constant, a log normal will always close down. Now, also the concentration profile, as I will show you in a practical application, can be used, for example, to have an educated guess about the threshold level for the existence or for the presence of fat tails in the data. Why? Because you can imagine that if the distribution we are considering, so if the phenomenon we are modeling is not something that we can describe with a pure Pareto or a pure power law that would correspond to just the straight line in the concentration profile, but it's a combination, so it's maybe a mixture of two distributions, so a distribution from the bulk and a distribution for the tail. What you will see is that your concentration profile will have some sort of behavior, but when the fat tail kicks in, so when the fat tail manifests itself, it becomes horizontal. So a way of finding the threshold using the concentration profile is to look at the part of the plot for which the horizontal constant behavior appears in the plot. As I will show you with actual data in the subsequent parts of this lesson, this is a further heuristic that we can use for identifying the threshold. And if we combine this heuristic together with the ZIF plot and the mean excess function plot, we already have a quite reliable starting point for the analysis we are going to continue. For more information about the concentration profile, I will just refer you to my paper, so you find there all the information, all the interpretations, and all the properties of the concentration profile, and also additional measure like the concentration adjusted expected shortfall, and so on. What is important to stress in any case is that the truncated Gini is strictly connected with the expected shortfall and the valid risk. Why? Because if you consider the truncated Gini is the Gini of all the observations above a given threshold that we can express in terms of a quantile. But quantiles are nothing more than what in finance we call valid risk. So the concentration profile connects the truncated Gini with a given truncation, which is the valid risk, and the expected shortfall is nothing more than the expectation of all the observations above the valid risk. So we can always use the Gini truncated at the valid risk level as a extra measure of variability above the bar, and a measure of variability that, together with the expected shortfall, gives us information about the behavior of a tail.